Can you hear me? So let me start. My name is Keiji Saito from Keio University in Japan. And today I talk about some aspect in eigenstate thermalization from the viewpoint of last time. So my collaborator is Tomotaka Kuwahara from Riken. And so this is a plan of my talk. First two part is a kind of review, which is necessary to my talk. And from third part, I talk about the eigenstate thermalization properties for the system which has clustering property when the system in equilibrium. Okay. So before going to the central part of my topic, let me fix the setup and so on. So the setup is kind of rather general. So we consider one-dimensional. Most of part, I think about one-dimensional systems which has size n. Small n is a notation for indicating the system size in my. Please keep it. And I assume that the Hamiltonian is decomposed into the local part like this. So we assume that the spectral norm of the local Hamiltonian is order 1. So if you think about the Heisenberg chain, it's a standard. The local Hamiltonian is just a local Heisenberg interaction. So another important quantity is observable. I use a notation omega. Again, I assume that observable is decomposed into the local part. This, when you consider total magnetization as a target observable, of course, this can be decomposed into the magnetization at each side. So we think about this kind of setup. And in general, thermalization study, they think about the expectation value of observable in time. And we ask how similar it is to the thermal value. More precisely, the thermalization property can be classified into several subjects. Roughly speaking, we have the 3 subjects. First is the equilibration, and the second is the steady state properties, and the third subject is the eigenstate properties. Equilibration, they study the relaxation. Expectation starts from some initial state and eventually goes to some values. Whatever the saturated value, in this subject, they consider the relaxation properties, initial time dependence and fluctuation and so on. The next subject is the steady state property. Starting from the initial state, it goes to some values. The question is what is this value? How similar it is to the thermal value? And how fluctuating. This kind of thing is a target, this subject. And another important subject is the eigenstate properties. You know, the most important thing is the ETH, eigenstate thermalization. In eigenstate thermalization, most important property is ETH, and ETH is divided into 2 classes. Previous speaker, Sagawa, explained more detailed classification, but I talk about the simple classification, strong or weak. In my talk, I talk about ETH. So although people here already talk about the ETH, just in case for consistency, let me explain about what ETH is. So we are thinking about the expectation value of the omega. This is the expectation value for eigenstate. E is the eigenstate of the Hamiltonian with eigenvalue E. Okay? And omega beta is the equilibrium expectation value with inverse temperature beta. And temperature is determined so that expectation value of Hamiltonian is equal to E. E is the eigenvalue of the. We put 1 over n so that total quantity is the order of local size. And what strong ETH states is that this quantity eventually goes to 0 in the thermodynamic limit. We don't think about the off-diagonal version in my talk. We care about the diagonal version. This is the diagonal version of ETH. Then this strong ETH is connected to the steady state properties in the following way. And suppose we take initial state from the small energy shell like this, then you can eventually get this expression for a long time limit. This is a long time limit. This is the expression for the non-integrable systems, so that spectrum has no degeneracy. And assuming the strong ETH, immediately you get the thermal value. And we can say that strong ETH guarantees that the steady state is thermal values. Like this is very important. And one point is that so far everybody studies on the high temperature regime. Strong ETH is thought to be valid for high energy regime, which is the center of the spectrum, and it's valid for the non-integrable systems. This is one comment. So let me briefly explain about weak version of ETH. So let's think about the small energy shell with energy width delta. So we consider again expectation value for eigenstate E, and we calculate also a microcanonical value within this energy shell. In general, this quantity may deviate from microcanonical value. The question is, what is the statistics of the deviation? The statistics of the deviation can be characterized by variance, which formulated like this. Here, calligraphic n is the number of eigenstates within this energy shell. Okay? So what weak ETH tells us that this variance goes to 0 in the thermodynamic limit. So this weak version of ETH is rather general for general systems, especially for high temperature regime, center of the spectrum. This means even integrable system satisfies it. Because variance goes to 0, this means huge number of thermalized state exists even in this energy shell. But this energy shell has exponential large number of eigenstates, and this means also a huge number of non-thermalized states should exist. So let me show you some numerical calculation performed by Alba. So he thinks about the Heisenberg model, XXX model, and he calculated using the Bethe-Ansatz approach. He calculated the reduced density matrix for two adjacent local sites. And he also calculated the average of the reduced density matrix for two sites within this energy shell. He compared how deviation, he studied how deviation exists in this energy shell. So he compared the variance for each matrix element of reduced density matrix. The results looks like this. He plotted as a function of the system size. This graph tells us that typical system size behavior of the variance is 1/n, the typical system size dependence. Later, I go back to this dependence, so please keep in mind. So my talk. So in my talk, I'd like to raise the following questions. So suppose we start with very general property of the system that even integrable system have. Then what can I say about thermalization properties? As such general property, I choose clustering property. What is a clustering property? Everybody knows here. Clustering property simply means that exponential decay in equilibrium correlation. This is a very general system, but this is the equilibrium property. My concern is about the thermalization for isolated system, but we consider the system which has a clustering property when the system is in equilibrium state. So mathematically, you can formulate it like this. OX is a local operator at site X, and if you think about equilibrium correlation, it shows the exponential decay with the correlation length for a sufficiently large distance. This is the description. Supposing these properties, my question is, what can I say about the thermalization? So let me stress about the generality of the clustering. Indeed, clustering property is very common general systems, except to the critical point. Of course, at phase function point, the correlation should power or decay, so it is exceptional. But except to the critical point, generally clustering property is valid. So, for example, one-dimensional system mathematical physicists are lucky rigorously show any homogeneous, rigorously show the clustering property for any homogeneous one-dimensional systems. For example, one-dimensional Ising model you can show easily correlation length. Correlation length follows this temperature dependence. But it's finite as long as beta is finite. So another thing that I want to stress is that even low temperature, it is satisfied in general. Both system has phase transition at certain temperature. Even below phase transition, clustering property is satisfied. So it's quite robust property. And another thing that I want to stress is that even integrable system also show clustering property, quite general. So starting with this general property, what can I say about, I think, eigenstate thermalization? The question. Maybe it's okay. Okay, so before going to central part of my central result of my talk, let me make first guess about my question. So first guess is the following. We impose a very general property, which is a clustering property. Because this is general, this means that our target system is thermodynamically general. So as long as high temperature regime is concerned, we expect that we can derive this weak version of ETH. This is something expected. But on the other hand, our condition is too general. Even integral system is satisfied. This means strong ETH cannot be derived with this simple condition. So on the other hand, as we noticed, weak ETH means huge number of thermalized states exist in this energy shell. So the new question arises. What happens if you consider low density of state regime? Does the number of thermalized states remain huge number, or the number of thermalized states decreasing proportional to the density of the state? This is a non-trivial question. I cannot answer to this question immediately. The concern is the compatibility of low density of state and clustering property. We can consider the gapped system. This is possible if we consider gapped system. The typical density of state behavior for gapped system is look like this. N to the N is the system side and N to the constant times energy. This is a typical density of state behavior. We look at the low temperature regime for gapped system. Gapped system guarantees that even ground states satisfy the clustering property. Even ground states satisfy the exponential correlation from the theory by Hastings and Connor. And this behavior, concerning this behavior, as long as low line energy excitation is described by local excitation picture, we can derive this kind of density of behavior for density of states, as argued by Hastings. So having in mind such systems, we can calculate the property of thermalization property, thermalization, eigenstate thermalization. Okay. So let me explain our result. Our result has two things, depending on the low temperature regime and high temperature regime. So about low temperature regime, suppose that at low energy regime, low temperature regime, the system has a clustering property, having in mind the gapped system. And in addition to this, density of state behaves like this. System times to the power of sometimes energy. Suppose this density of state satisfied, then you can show that strong ETH holds. This is a result for the low density of state regime. And another regime, high temperature regime. So as long as one-dimensional system concerned, as I said, Araki showed that homogeneous system shows clustering property. So this is automatically satisfied if you the homogeneous system. But our system is arbitrary. Inhomogeneous system is also included. In this case, supposing this condition, we can show weak version of ETH holds. And variance is bounded by this functional form, like this. So remember about the numerical demonstration by Alba. I said that numerical simulation shows that variance is decays 1 over n in the large system size. So our band is similar up to the logarithmic correction, logarithmic term. In addition to this, we can show ensemble equivalence between microcanonical distribution and canonical distribution for very small energy window. So this you can take very small, which is exponentially small with respect to the system size. Have exponential. This is the result. So the second part is a more or less quantitative upgrade for a known result. But first part is conceptually new. So let me show you some example which shows this. Yes, I show you the specific model with this integral model. The most trivial system is independent spin, actually. Independent spin is automatically clustering properties satisfied because by definition, uncorrelated. And low-lying excitation is given by flipping the spin. Then everything, any condition is satisfied, then strong ETH holds. But this is too trivial. What I want to say that this statement is very general, universal, whatever the non-gravity, whatever the system, whatever the modification of the network. In this sense, it's universal. So let me show you less trivial example, which is interacting system. So as I said, clustering property is valid even for integrable system. Then we take the integrable Hamiltonian, which is a transverse ID model. So this Hamiltonian can be diagonalized with Jordan-Wiener transformation with fermionic operator C. Then H is a magnetic field. We set H larger than 1 so that the system has gap between the ground state and the excited state. Then because the system has gap, even ground state is shows clustering properties. And the finite temperature regime from the theory by Araki automatically clustering properties proven. So concerning the density of state, we can make a rough estimation in the following way. So suppose in momentum direction, local excitation picture, we consider the number of excitation. We consider the number of excitation, J excitation. The number of J excitation can be counted by combinatorial Nj, and J times gap is roughly speaking energy. And this estimation immediately gives us this behavior, system side behavior. This is a rough estimation to get this system side dependence of the density of states. Okay? So this behavior is very common in gap system as long as local low-lying excited energy is given by local excitation picture. This case, local means local in the momentum space. So one non-trivial case is AQT model. AQT model is a non-integral system having energy gap between the ground state and the excited state. Even for this case, these people showed that low-lying excitation is given by local excitation picture. So the density of states should obey this size dependence. Okay. Yeah, maybe it depends on the systems, but as long as a one-dimensional system, this picture is very, very general. Not general, but it's very quick. Yeah? Okay, okay. I want to say that many examples exist about this. Yes. Yes, we are thinking about low energy regime. We don't think about the high temperature regime. High temperature regime.
You can wait.
Okay, this is the Hamiltonian. Okay, so I want to demonstrate clustering property using the mutual information. So I calculated mutual information for the side I and side J. Mathematical definition of mutual information is given by this using channel entropy. And so for equilibrium distribution with certain temperature, we can demonstrate the exponential decay of mutual information as a function of distance, I minus. This showed clearly exponential decay. From this exponential decay, we can extract the information of correlation function as a function of inverse temperature. Okay? As you see, the correlation length is finite even for large beta. This means even for low temperature regime, clustering property is valid. Okay? This is a one demonstration property. Okay, so now most important picture that I want to show with this model. So this is a spectrum picture. This is a ground state and excited state. And we take 100 excited state from the 100 excited state, and we call this set epsilon S. Then we take an eigenstate from this set. So I define this function considering the total magnetization as target observable. We consider the expectation value for eigenstate from taken from the set epsilon S. And we also calculate the expectation value of magnetization for ground state. And this should deviate in general. And we compare the deviation. And we consider this function considers the maximum value of deviation from doing this. And the result looks like this as a function of system size. So this maximum deviation decreases as increasing system size. This shows that as long as you think about the expectation value of local observable, excited state behaves like ground state. In this sense, strong ETH holds. Another example is about the reduced density matrix. I calculated the reduced density matrix for 2 adjacent local sites. Okay? So E is a reduced density matrix for excited state taken from the set epsilon S. We take 100 against it. And so there is a reduced density matrix for the ground state. And we compare the distance, calculating the trace distance. And G is the maximum value of the distance within this, this set. The result looks like this. As a function of system size, again, you see that like, this maximum value of distance decreases in the as increase the system size. This tells us that, again, that as long as we consider expectation value for reduced density matrix, any excited state behaves like ground state. In this sense,
here you are fixing the number of excited states.
Yes, unfortunately, yes, because of limitation of
the zero temperature, strong energy.
Yes. It's a special version of ETH. It's not common. It's not general ETH. No. Yeah, zero temperature, but it can be finite, extremely low temperature. Yes, in a sense, yes. But strictly speaking, yes. Yeah. In my definition, it's a strong ETH. It depends on the definition, maybe. Okay, so let me briefly show you outline of the proof, especially for the strong ETH for low temperature regime. Okay, so we start with the clustering property. AX is an arbitrary operator for the subset X. And this equilibrium correlation is bounded by exponential decay for sufficiently large distance. Yes, but no, taking sufficiently large distance, norm can be 1. Okay. So
there is a constant.
Yes. Sorry. Well, I fixed the norm 1. Yes, so you're right. From this condition, you can derive the bound for the mth moment for equilibrium correlation, equilibrium distribution. So the mth moment, arbitrary mth moment for this equilibrium distribution is bounded from above by this. So far, we consider about the one-dimensional systems, but this at the level of proof, we can generalize up to any dimensional systems. So we put we consider d-dimensional system. D is a dimension. C1 and C2 is some constant. N is a system size, and xi is a correlation length. So in addition to this, we consider the mth moment, arbitrary mth moment for the eigenstate. And using simple calculation, you can find that mth moment for eigenstate is bounded from above by using the mth moment for equilibrium distribution. Now we use this bound. Plugging this bound into this, you can make bound this quantity from above using the clustering parameter. So in addition to this, we consider the distribution, which is defined like this. So this is the distribution of target to observable omega in terms of eigenstate E. Okay? Once you have property of this distribution, you can calculate everything. Okay, so what you can prove is that this has concentration bound. What concentration bound means that the tail of distribution is exponentially decays. You can prove this exponential decay using this bound. So now we have the concentration bound for the distribution, and we calculate this guy. This guy is reformulated by using distribution P, and we know the concentration bound for this distribution. Using this, we can make a bound for this quantity like this. So far, we don't say about the choice of inverse temperature. So now we relate inverse temperature to system size dependence like this. This means in the thermodynamic limit, beta goes to infinity. This means this expectation value is the expectation value for ground state. Okay, and by putting the information of density of state for this, then immediately you get that B1 and B2 is convergent in the thermodynamic limit, and so the right hand side vanishes in the thermodynamic limit. This is the ETH. So let me summarize. So we consider the system having class-line property, which satisfies even for low temperature regime. And strong ETH can be proven for the density of state, for gapped system, especially for the gapped system. As I said, this is very general and universal. Concerning the high temperature limit, high temperature regime, we can show weak version of ETH, and variance is bounded by this system size dependence. And I also proved that eigenstates ensemble equivalence holds for exponentially small energy shell. So this is my talk. Thank you for attention. Actually, this is this is not 1 over n, but 1 over n squared. No, 1 over n square root. So it's okay. Okay, so yes, I don't talk about this with numerical calculation. What I showed is only about low temperature regime. I don't think about high temperature regime. I don't check about this dependence. Yes. Logarithmic correction is difficult to see. So I believe that 1 over n logarithmic correction is impossible to see even in the Alba's demonstration, Alba's numerical calculation that I showed in the talk. It showed he showed 1 over n dependence, but it's impossible to see logarithmic correction, even if it exists. It's impossible to see.
PPTH at n.
Yes. Actually, it's very hard to say. It's a.
Is it? Oh,
Yeah. Yes.
so I you said you proved bound for bound.
You? No, I don't. No, you. What?
What's the
How?
previous result?
N to power 1/4 over 1. Quantitatively, this bound is up. Yes, strictly speaking, yes, I agree. But in my definition, it's a. Huh? But it's a matter of definition.
Copyright.
Thank you very much.